Okay, in this section we're going to take a look at improper integrals. So let's just go back and review what is meant by a definite integral. And there are some conditions on definite integrals, such as a and b have to be real values, and the function f of x has to be defined on this closed interval. So if we look at an integral like from 0 to 1 of 1 over root x dx, this is not defined at that endpoint, at x is equal to 0, so that would be a problem. Or for the function from 0 to pi over 2 of tan x dx, this of course is not defined at x equals pi over 2. And on the interval from -1 to 1, we've got the function 1 over x cubed. Well, this is perfectly fine at 1 and -1, but it has a problem that it's not defined in the middle of that interval, specifically at x equals 0. So in this section, again, we're going to take a look at some tools to help us work with some of these integrals and integrals that are somewhat like this. So let's start off with a definition, which is if a function f is continuous on your interval from a to infinity, so here's your integral from a to infinity of f of x dx, this is an improper integral. We're going to define that integral as the limit as b goes to infinity of the definite integral a to b of f of x dx. Of course, this is provided that the limit exists and is real, then it converges. Otherwise, it is divergent. And similar to this, if we had an integral from infinity to b or negative infinity to b, and you took the limit as a went towards negative infinity of a to b of f of x dx, you could find out whether or not this converges or diverges as well. So let's try a few examples. So in this case, we have the integral from 1 to infinity of 1 over x dx. So let's change this to the form of the limit as b goes to infinity of, positive 1 to b, 1 over x dx. And this is the same as the limit as b goes to infinity. And I can calculate this. This function here becomes ln absolute value of x evaluated between b and 1, and that becomes, again, we need to keep the limit as b goes to infinity. This becomes ln b minus ln 1, and you should be able to see from this that now when I substitute b going towards infinity and apply this limit, I get that this becomes infinite, therefore it diverges. From a picture, what we're doing is taking this function y equals 1 over x, and we're starting at 1, and we're adding up the area all the way to infinity. And even though the area is getting closer and closer and closer to 0, this is an infinite amount of area that is in here. Now let's compare that to this example, where I have an integral from negative infinity to 0 of ex dx. So the limit as a goes towards negative infinity, and change this to a and 0 of ex dx. Apply my integration and get e to the x being evaluated at 0 and a, gives me the limit as a goes towards negative infinity of e to the 0, which is 1, minus e to the a. And so in this case, I apply the limit to each piece. The limit to the first piece is 1, and as this a value gets closer and closer to negative infinity, e to the negative infinity is the same as 1 over e to the infinity, so this gets closer and closer to 0, and this one actually converges to the value of 1. And from a graphical point of view, I've got an e to the x function, yeah, and interesting to the exact value of 1. So what happens if we have an infinite limit, an area or bound that's infinite on each side? Well, I can split this up so that I think about it as two integrals, one from negative infinity to 0 and the other one from 0 to infinity, and I can go and calculate these two pieces. However, if we do that, we will find that the limit as b goes to infinity of the integral from 0 to b of 4x cubed dx, well, the integral is x to the fourth evaluated from b and 0, and we apply the limit as b goes to infinity and substitute in the b to the fourth and apply the limit again as b goes to infinity. You'll see that this side is infinite, and what happens with an improper integral when you split it like this is that if either piece is divergent, which the second piece is, then the entire integral is divergent. So we say therefore this diverges. Let's take a look at one last example. The integral from 0 to infinity of e to the negative 3 dt. So we'll set our limit as b goes to infinity of the integral of 0 to b, e to the negative 3t dt, and of course we need a u sub, so the u is negative 3t, and u therefore is equal to negative 3 dt, and dt would be du divided by negative 3. And so this limit as b goes to infinity, with the substitution for dt, I can pull out the negative 1/3 to get it into du's. So I get negative 1/3 limit as b goes to infinity of the integral from, now I have to change these the limits of integration, so those were t values, the u values are negative 3 times the t value, so the a value becomes 0 and the top value becomes negative 3t, e to the u du, and I can keep this negative 1/3 and keep the limit as b goes to infinity, and then put in e to the u being evaluated at negative 3b and 0, and substituting in negative 3b in gives me the same negative 1/3 limit as b goes to infinity, and now of e to the negative 3b minus e to the 0, which is 1, and then I can apply the limit to these two pieces, and so the limit applied to the first piece becomes equal to 0. The limit applied to the second piece becomes negative 1, and I get negative 1/3 times negative 1, which is equal to 1/3.